The moment the grid fails, it doesn't collapse with a dramatic explosion or a warning siren. It dies quietly. A flicker, a hesitation in the hum of your refrigerator, the sudden silence of distant traffic signals, and then nothing. Within seconds, an entire system that modern civilization depends on ceases to function. What most people misunderstand is that power outages are not just about darkness. They are about the immediate loss of coordination, communication, and control. Electricity is not merely a convenience, it is the bloodstream of infrastructure. When it stops, everything else begins to destabilize in a predictable, cascading sequence that has been studied extensively in emergency management models but rarely understood at the household level. The real danger begins not in the first hour, but in the invisible dependencies that unravel next. Water treatment plants rely on electrically powered pumps and chemical dosing systems. Without them, clean water supply begins degrading within hours. Telecommunications towers, often assumed to be resilient, depend on battery backups that typically last between 4 to 8 hours under load. After that, even if your phone still has charge, it becomes a disconnected device. Refrigeration fails, and food safety timelines begin ticking immediately, governed by microbial growth curves that double contamination risk every 20 minutes in the danger zone, between 5 degrees C and 60 degrees C. What appears to be a simple blackout is, in reality, a synchronized failure across interdependent systems. Most people assume that backup generators are the solution. This is the first critical misunderstanding. Generators are not independence, they are dependency shifted to another fuel source. They rely on gasoline, diesel, or propane supply chains that themselves depend on electricity for pumping, refining, and distribution. During large-scale outages, fuel availability becomes constrained not because it doesn't exist, but because the infrastructure to deliver it is impaired. Historical data from major blackout events shows that fuel stations often cease operation within hours, even if underground tanks remain full. The limitation is not supply, but accessibility. The overlooked principle here lies in energy autonomy versus energy substitution. Substitution replaces one vulnerable input with another. Autonomy removes reliance entirely. This distinction is rooted in systems engineering, where resilience is defined not by backup capacity, but by the ability to operate independently of external inputs for extended durations. True off-grid setups are not designed for convenience. They are designed for continuity under constraint. They are governed by energy balance equations, storage efficiency, and load prioritization strategies that mirror those used in remote scientific outposts and spacecraft systems. To understand what must be built, you have to start with the physics of energy itself. Every electrical system is constrained by 3 core variables: generation, storage, and consumption. Most households only think about consumption. Off-grid survival demands a reversal of perspective. You must first calculate your minimum viable energy requirement, the absolute baseline needed to sustain critical functions. This includes water purification, minimal lighting, communication devices, and, if applicable, medical equipment. Not comfort, not convenience, survival. The hidden science that most overlook is that energy systems fail not because of insufficient generation, but because of mismanaged storage and inefficient load distribution. Batteries are not simply containers of power. They are governed by charge cycles, depth of discharge, temperature sensitivity, and conversion losses. A poorly designed battery system can lose up to 30% of its stored energy through inefficiencies alone. Lithium iron phosphate batteries, for example, offer higher cycle life and thermal stability compared to traditional lead-acid batteries, but they require precise charge controllers to prevent degradation. Without proper regulation, even the best battery becomes unreliable. Solar panels are often presented as the ultimate solution, but their effectiveness is misunderstood. Solar generation is intermittent and variable, dependent on geographic location, seasonal angle, and atmospheric conditions. The peak output rating of a panel is almost never achieved in real-world conditions. What matters is not peak wattage, but average daily energy yield, which can be as low as 20–30% of rated capacity in suboptimal conditions. This means that a system designed based on peak output will consistently underperform when it matters most. Evidence from off-grid communities and remote installations shows that the most resilient systems are not the largest, but the most balanced. They integrate multiple small-scale generation sources with efficient storage and strict load management. Wind turbines, while less predictable, can complement solar by generating power during low-light conditions, particularly at night or during storms. Microhydro systems, where available, provide continuous baseline generation with minimal fluctuation. The principle is diversification, not reliance. The survival implication is clear. A single-source system is a point of failure. A multi-source system, even if individually weaker, creates redundancy that dramatically increases reliability. This is not theory. It is observed behavior in distributed energy networks where decentralized systems outperform centralized grids under stress conditions. The same logic must be applied at the individual level. But energy is only one layer. The second layer is conversion and distribution. Direct current DC systems are inherently more efficient for storage and low-power applications, yet most household devices operate on alternating current AC. Every conversion from DC to AC introduces losses, typically around 10–15%. In an off-grid scenario, these losses accumulate quickly. The hidden advantage lies in using DC-compatible devices wherever possible, reducing conversion steps and preserving stored energy. Most people also fail to account for phantom loads, devices that consume power even when turned off. These small, often unnoticed draws can drain a battery system significantly over time. Studies have shown that phantom loads can account for up to 10% of total household energy consumption. In a grid-dependent environment, this is negligible. In an off-grid system, it is critical. As the blackout extends into days, the situation escalates beyond energy. Water becomes the next critical bottleneck. Without electrically powered pumps, municipal systems lose pressure, allowing contaminants to enter through leaks and fractures in aging infrastructure. Boiling water becomes necessary, which introduces a new demand on energy resources. This creates a feedback loop. Energy is needed to secure water. But water is needed to sustain the human body that manages the energy system. The transition here is not gradual, it is abrupt. Within 72 hours, the majority of urban populations begin to experience compounding failures: food spoilage, water insecurity, communication breakdown, and increasing environmental stress. Emergency services become overwhelmed, not because they are ineffective, but because their operational models are designed for localized incidents, not systemic collapse. The critical insight is that survival is not about reacting to failure. It is about preemptively designing systems that do not fail under the same conditions. This requires a shift from consumption-based living to system-based thinking. Every component must be evaluated not for its performance under normal conditions, but for its behavior under constraint. And this is where most off-grid setups fail, not because they lack technology, but because they lack integration. A solar panel without adequate storage is useless at night. A battery without efficient load management depletes too quickly. A generator without fuel becomes dead weight. True resilience emerges only when each component is designed to support the others in a closed-loop system. The next phase of understanding goes deeper into the architecture of these systems, how they are physically structured, how they interact, and how they can be scaled without introducing new vulnerabilities. Because the real threat is not just the blackout itself. It is the prolonged instability that follows, where temporary solutions break down and only truly independent systems continue to function. As the outage stretches beyond the initial shock phase, the system you rely on is no longer the national grid. It is whatever you have built, intentionally or unintentionally, inside your own environment. This is where architecture becomes the deciding factor between temporary adaptation and sustained survival. Most people imagine off-grid systems as add-ons, external units bolted onto an otherwise unchanged lifestyle. This is the second major misunderstanding. In reality, the most resilient setups are not additions, they are reconfigurations of how energy, water, and essential resources flow through a space. The structure itself becomes part of the system. The hidden principle here is load hierarchy, a concept borrowed from critical infrastructure engineering. Not all electrical demands are equal, and treating them as such creates inefficiency and failure. In a blackout scenario, every watt becomes a strategic decision. Lighting, for instance, is often overestimated in importance. Modern LED systems can provide sufficient illumination at extremely low power levels, often under 10 watts per room. Compare that to refrigeration, which can draw hundreds of watts intermittently, or water pumping systems that spike significantly during operation. Without a defined hierarchy, systems become overloaded not by necessity, but by poor prioritization. This is where circuit segmentation becomes critical. Instead of powering an entire household through a single distribution line, advanced off-grid setups divide circuits into essential and non-essential branches. Essential circuits are isolated and supplied directly from the most stable energy sources, often with dedicated battery reserves. Non-essential circuits are either disconnected or supplied only during surplus generation periods. This approach mirrors hospital-grade electrical systems, where life support equipment is separated from general-purpose power to ensure uninterrupted operation under failure conditions. Evidence from disaster-resilient housing projects shows that segmented systems reduce energy waste by up to 40% while increasing operational duration during outages. The reason is simple: energy is no longer diluted across unnecessary loads. It is concentrated where it matters most. This concentration effect is what transforms a limited energy supply into a sustainable one. But architecture is not just electrical. Thermal dynamics play an equally critical role, and this is often completely ignored in conventional planning. When the grid fails, climate control systems, air conditioning, heating, ventilation cease to function. What remains is the passive thermal behavior of the structure itself. Buildings with poor insulation rapidly equalize with external temperatures, creating dangerous conditions in both extreme heat and cold. The human body has a narrow thermal tolerance range, and prolonged exposure outside this range leads to physiological stress, dehydration, or hypothermia. The overlooked science here is thermal mass and insulation synergy. Materials like concrete, brick, and water have high thermal mass, meaning they absorb and release heat slowly. When combined with proper insulation, they create a buffering effect that stabilizes indoor temperatures over time. This is not theoretical. It is the reason traditional desert and Arctic structures can remain habitable without active climate control. In an off-grid context, this principle becomes a survival multiplier. A well-designed space can reduce the need for energy-intensive heating or cooling by maintaining a more stable internal environment. Ventilation is another critical factor, but not in the way most assume. Opening windows for airflow can actually increase thermal load during extreme heat, introducing hot air that raises indoor temperatures. Controlled ventilation, using cross-flow design and shaded intake points, is far more effective. The goal is not maximum airflow, but optimized airflow, directing cooler air through the structure while minimizing heat gain. This requires an understanding of pressure differentials and airflow dynamics, concepts rarely considered outside of engineering disciplines, but essential in a grid-down scenario. As the blackout persists, the focus shifts from maintaining systems to sustaining resources. Water again becomes central, but now in terms of storage and purification rather than supply. The common assumption is that storing large quantities of water is sufficient. This is partially true, but incomplete. Stored water is a finite resource, and without replenishment or purification capability, it becomes a countdown timer rather than a solution. The hidden layer is water cycling. In nature, water is never static. It moves, evaporates, condenses, and filters through multiple stages. Replicating even a simplified version of this cycle dramatically increases sustainability. Rainwater harvesting systems, when properly designed, can capture significant volumes even in moderate rainfall conditions. The efficiency of these systems depends on catchment area, surface material, and filtration stages. A clean roof surface, for example, can yield thousands of liters of water annually, but without first flush diverters and filtration, that water carries contaminants that make it unsafe for consumption. Filtration itself is often misunderstood. Boiling water addresses biological contaminants, but does nothing for chemical pollutants or heavy metals. Mechanical filtration systems, such as ceramic or activated carbon filters, remove particulates and certain chemicals, but their effectiveness depends on pore size and maintenance. The most resilient approach combines multiple methods: sedimentation, filtration, and disinfection, creating a layered defense against contamination. This multi-barrier strategy is the same principle used in municipal water treatment, scaled down for individual use. Evidence from field studies in disaster zones shows that waterborne illness becomes one of the leading causes of mortality within the first week of infrastructure failure, not because water is unavailable, but because it is unsafe. This distinction is critical. Access without safety is a hidden risk that compounds over time. Food systems follow a similar pattern. The initial focus is on storage, non-perishable items, preserved goods, caloric density. But as time extends, the limitation becomes not quantity, but diversity and nutritional balance. The human body requires more than calories. It requires micronutrients, electrolytes, and hydration balance. A diet based solely on stored carbohydrates leads to deficiencies that impair cognitive and physical function, reducing the ability to manage the very systems required for survival. The overlooked principle here is low-energy food production. Sprouting, for example, requires minimal resources and can produce nutrient-dense food within days. Microgreens, grown with limited water and light, provide essential vitamins that are otherwise absent in stored food supplies. These methods do not replace large-scale agriculture, but they extend nutritional viability in constrained environments. As these systems interact, energy, water, food, and structure, they form a closed-loop ecosystem. Each component supports and stabilizes the others. This is the core of true off-grid resilience. It is not a collection of independent solutions, but an integrated network designed to function under continuous stress. The escalation becomes clear as time progresses. Temporary fixes degrade, supplies diminish, and external support remains uncertain. What determines outcome is no longer access to resources, but the efficiency and adaptability of the systems in place. Small inefficiencies compound into critical failures. Minor design flaws become major vulnerabilities. And this leads to the next layer of the problem: maintenance and degradation. Because no system, no matter how well designed, operates indefinitely without intervention. Components wear out, filters clog, batteries degrade, and environmental conditions shift. The question is not whether systems will fail, but how predictably and how recoverably they do so. Understanding this requires moving beyond setup into lifecycle management, where the focus is not just on building the system, but on sustaining it over time under resource constraints. Because in a prolonged blackout, survival is not a static state. It is a continuous process of adaptation, repair, and optimization. As the blackout extends into weeks, the defining factor is no longer what you have built, but how long it continues to function without external input. Every system begins to reveal its limits. Batteries lose capacity with each cycle, not suddenly, but through gradual chemical degradation driven by temperature, depth of discharge, and charge rate. A lithium iron phosphate battery rated for thousands of cycles can still fail prematurely if consistently overdischarged or exposed to thermal stress. This is not a flaw in the technology, it is a consequence of electrochemical reality. Energy storage is never permanent, it is a managed decay process. The objective is not to stop degradation, but to slow it to a rate that remains functional within your survival window. The misunderstanding at this stage is the assumption that redundancy alone guarantees reliability. Multiple batteries, extra panels, spare components, these create capacity but not necessarily resilience. True resilience is defined by recoverability. When a component fails, can the system adapt without collapsing? This is where modular design becomes critical. Systems that are built as monolithic units tend to fail catastrophically, while modular systems fail in isolation. A single faulty battery in a parallel bank, for example, can drain the entire system if not properly isolated. With correct design, using fusing, battery management systems, and segmented arrays. Failure is contained rather than propagated. The hidden science governing this behavior lies in feedback loops. Every system, whether electrical, thermal, or biological, operates through feedback mechanisms that either stabilize or destabilize it. Negative feedback loops regulate and maintain balance, while positive feedback loops amplify deviations, often leading to collapse. In an off-grid environment, uncontrolled energy consumption acts as a positive feedback loop, accelerating depletion. Controlled load shedding, on the other hand, introduces negative feedback, stabilizing the system by reducing demand as supply diminishes. This is the same principle used in large-scale grid management, scaled down to the individual level. Evidence from long-duration, off-grid installations shows that the most successful systems are not those with the highest capacity, but those with the most responsive control. Smart charge controllers, manual load prioritization, and continuous monitoring allow for dynamic adjustment based on real-time conditions. Without this, even a well-designed system drifts toward inefficiency and eventual failure. The key variable is not energy itself, but information, knowing how much energy is available, how quickly it is being consumed, and where it is being lost. As time progresses, maintenance becomes the central challenge. Filters clog with particulate matter, reducing water flow and increasing the energy required for purification. Solar panels accumulate dust and debris, decreasing efficiency by measurable percentages that compound over days and weeks. Mechanical components experience frictional wear, especially in improvised or heavily used systems. The assumption that these issues are minor leads to a gradual decline that often goes unnoticed until it reaches a critical threshold. The overlooked principle is preventative maintenance under constraint. In normal conditions, maintenance is reactive, components are repaired or replaced after failure. In a prolonged blackout, replacement is often not an option. This shifts the strategy entirely. Components must be preserved before failure occurs, extending their functional lifespan as much as possible. Cleaning solar panels regularly, managing battery charge cycles carefully, and rotating water filtration elements are not optional tasks. They are survival actions that directly influence system longevity. Water systems, in particular, begin to show stress under extended use. Stored reserves diminish, and reliance shifts increasingly toward purification and collection. Rainfall variability introduces uncertainty, and filtration systems must handle higher loads. Biological growth within storage containers becomes a risk, especially in warmer climates where microbial activity accelerates. This introduces a new layer of complexity, maintaining water quality over time, not just achieving it initially. The use of opaque containers to limit light exposure, regular agitation to prevent stagnation, and periodic disinfection cycles become essential practices. Food systems follow a similar trajectory. Stored supplies deplete, and reliance on low-energy production methods increases. However, these methods are not immune to failure. Sprouting systems can become contaminated if not properly cleaned. Microgreen cultivation depends on consistent moisture and light conditions, which may fluctuate as energy availability changes. Nutritional balance becomes increasingly difficult to maintain, leading to subtle but significant declines in physical and cognitive performance. This is not immediate starvation, but a gradual erosion of capability. The survival implication is that long-term resilience is not about abundance, it is about efficiency and adaptation. Every resource must be used with precision, every process optimized to minimize waste. The margin for error narrows over time, and small inefficiencies that were previously insignificant become decisive factors. As the external environment continues to degrade, supply chains remain disrupted, infrastructure unrepaired, and recovery timelines uncertain, the internal environment you have created becomes your entire operational world. This is where psychological factors begin to intersect with physical systems. Decision fatigue, stress, and uncertainty can lead to poor judgment, which in turn affects system management. Overuse of energy resources, neglect of maintenance tasks, and misallocation of supplies often stem not from lack of knowledge, but from cognitive overload. The hidden connection here is that system simplicity directly impacts human reliability. Complex systems with multiple failure points require constant attention and precise management, increasing the likelihood of error. Simplified systems, even if less efficient in theory, often perform better in practice because they reduce the cognitive burden on the operator. This is a principle observed in high-risk environments such as aviation and space missions, where system design prioritizes human factors as much as technical performance. The final escalation is not a single event, but a convergence. Energy systems degrade, water systems strain, food systems narrow, and human capacity is tested simultaneously. What determines survival at this stage is not any single component, but the integration of all components into a stable, self-regulating system. This is the ultimate goal of an off-grid setup, not independence in the absolute sense, but controlled dependence within a closed loop. The critical insight is that resilience is not built in response to collapse. It is engineered in advance, through an understanding of how systems behave under stress, how they fail, and how they can be guided towards stability instead of breakdown. The grid, in its complexity, masks these realities by absorbing fluctuations and distributing risk. When it disappears, those responsibilities shift entirely to the individual system. And this is the reality most overlook. The blackout is not the event. It is the exposure of underlying dependencies that were always present but never visible. What you build off-grid is not just a backup, it is a replacement for an entire network of interconnected systems that normally operate beyond your awareness. When that network goes silent, the only thing that continues to function is what you have already prepared to stand on its own.